In this video, we're going to be looking at a phenomenon that occurs mostly in polyatomic ions, but also in any compound that has multiple correct Lewis structures. Firstly, let's do a review of formal charge because that's going to be important to understanding how this concept works. We'll start with the oxygens in nitrate that we see here. We know that oxygen atoms start with 6 valence electrons, so that's the start. We can see that the bottom 2 oxygens here have 6 lone pair electrons each that aren't involved in bonding, plus 1 bond, so 1 electron per bond. And if we do this calculation, we find that each of these oxygens have a -1 formal charge. Now, this is an example where not only can we show that this molecule has charge, we can isolate a specific atom that has the charge within the molecule. We can see that this oxygen here does not have that charge because if we do the calculation, oxygen starts with 6 valence electrons and there are 4 non-bonding or 2 lone pairs of electrons and 2 bonds, so 1 for every bond. We find that the formal charge of this oxygen is 0. Now, we know that the formal charge of NO3 is -1, so why are there 2 -1 formal charges? Well, we can find the answer by looking at the nitrogen. So nitrogen, we know, has 5 valence electrons to start. This nitrogen does not have any lone pairs, so 0. And it has 4 bonds, so 1 electron per bond. So what this means is that the nitrogen has actually lost an electron in forming nitrate, giving it a +1 charge. And if we add all of our formal charges together, -1 plus 1 is 0, minus 1 is -1, which matches the overall charge of the molecule that shows us that we have drawn this Lewis structure correctly. Now, one question that students might ask is, does the double bond always have to be in the top position, bonded to the or with the oxygen on top of the nitrogen, and do the negative charges always have to be on the bottom oxygens? Well, the obvious answer to this is no, and we can rationalize this using some fairly simple explanations about electrons. Point number 1, electrons never stop moving. Point number 2, electrons always want to move away from each other because of the repulsive force. Point number 3, if each of these oxygens have 6 electrons from 3 lone pairs, they really do not want to stay together. Which means, if we take 2 electrons, we can actually move them away. So if we take these 2 electrons and move them down here, we can turn them into a double bond, which is, again, also made of 2 electrons. Now, the problem here is that nitrogen, because nitrogen is smaller than elements that can make expanded valence shells, nitrogen cannot make 5 bonds. So how do we fix the problem that nitrogen has 5 bonds? Well, if we can take a lone pair and we can bring them down here and make a bond, is the opposite also possible? No, the answer is, of course it is. So if we take this bond here from the double bond and move it up to becoming a lone pair, we have just found one of the other possible Lewis structures that we can draw for nitrate, where now the double bond is down here in the bottom right position, and our negative formal charges are now over here. Now, if we follow this logically, there is a third structure that we can draw where we take 1 lone pair from the bottom left oxygen and bring it up to make a double bond, therefore causing one of the double bonds, or one of the bonds in this double bond, to break and turn into a lone pair on the bottom right oxygen. And if we are to draw that structure, it reveals the third possible Lewis structure that we can make. Now here, the obvious question is, which of these structures is the most correct? Well, again, the negative charge is always on oxygen, so we can't use negative charge on the most electronegative atom because the only thing that's changing positions is the double bond. So again, we can draw these two structures simply by moving the two electrons that make up the negative formal charge around the molecule. Now, if that's true, if the negative charge always falls on oxygen, that must mean that all of these structures are simultaneously correct. This is a phenomenon that we call resonance, in which we actually observe electron movement within a molecule that causes multiple structures to be possible at the same time. We can represent this with a special type of Lewis structure, which is what we call a resonance hybrid. We call it a hybrid structure because it is a amalgamation, or a hybrid, if you will, of the three different possible Lewis structures. So the skeleton of the structure is the same. We start by identifying the central atom and connecting all of the peripheral atoms to the central atom like this. But because this is a hybrid structure, we need to figure out which location to put the double bond and which location to put our lone pairs. So the rule for this is fairly simple. Only lone pairs that appear in all of the possible resonance structures, so in all three of the resonance structures, are shown. And bonds with full lines, I'll explain what that means, represent bonds that are found in all resonance structures. So what that means is that because this oxygen here has two lone pairs in this particular structure, but three in the other two, this oxygen here does not always have three lone pairs. This is true of every oxygen because every oxygen has one possible structure where it only has two lone pairs. So in our resonance hybrid, we would only draw a maximum of two lone pairs per oxygen to signify that each oxygen has a minimum of two lone pairs. Now, how do we show where the double bond is? Well, if the double bond is moving, we can't draw a full straight line in any location. So instead, we can use dotted lines like this. And what these dotted lines show is that sometimes in one of the possible Lewis structures we can draw, there is sometimes a bond that is here, but sometimes it is here, and sometimes it is here. So bonds with dotted lines represents bonds that are found on some, but not all, of the possible Lewis structures that exist. So another way of representing this is you're taking this one double bond and dividing it up between the three different locations, effectively saying that each location has 1 1/3 bonds because we're taking that double bond and splitting it over 3 locations, which is why we call this a resonance hybrid structure. Before we get to the final video of this particular section, you can see that all of the practice problems below are polyatomic ions, and in every single one of these polyatomic ions, you can draw multiple Lewis structures, or multiple contributing Lewis structures, which can then be combined in order to draw a resonance hybrid structure like the one that you see with nitrate. Until the next video, try a few of those as practice problems and see if you can get the hang of drawing hybrid structures.